that it stores n elements and that these operations take this amount of time. And now, what we're going to do is we're going to try to get a better understanding of why this data structure is actually impossible and it cannot exist. So another thing to note is that it is deterministic. There are two things. It is deterministic, and it supports ordered elements. So it can store elements that are comparable. That is the only requirement. Comparable elements. That's the only requirement it has. So it's not necessarily storing integers or anything. It's just storing things that can be compared with each other. That's it. And that might give you a hint as to why this data structure is impossible, which is essentially the big idea is we're going to figure out how can we use this data structure to do sorting with n comparable elements faster than n log n. And you guys probably remember from lecture, or hopefully you do remember from lecture, it is actually impossible to sort elements faster than n log n if the only thing you know about those elements is that you can compare them. So we did talk about radix sort, we talked about counting sort, which can sort faster than n log n. However, that's because those elements are taking advantage of the fact that we're sorting integers or we're sorting strings. Now, if you have an arbitrary collection of elements where the only thing you can ask is a less than b or is a bigger than b. If this is the only limitation, so you don't know what a and b are, you just know that you can compare them, then there is no faster algorithm than merge sort. Merge sort is the fastest algorithm that only relies on comparisons. Cool. So keeping that in mind, let's go ahead and jump into 1.1. So again, this one talks about trying to get a better understanding of Moose trees. And basically what we want you to do is we want you to complete the pseudocode and provide the running time and a short explanation justifying the running time as to your algorithm. And really what the pseudocode is doing here, if we zoom out a little bit and maybe make this bigger, is the goal is to take an array A of unsorted elements. So, A is our input. It's a vector of n comparable elements. So you don't know, they could be integers, they could be floats, they could be doubles, they could be many, many, many crazy things. And what we're going to want to do is we want to create a Moose tree out of them. That's it. And that's essentially what we're trying to do here is just create a Moose tree. So you can imagine the easiest thing to do is we already gave you the Moose tree. So it's empty. This creates an empty Moose tree. We iterate, for each element in A. So we grab each element, and then we Moose insert the element into our tree. That's basically it, because we're able to insert an element k. So I think maybe a better syntax here would be t.moose insert. But the syntax itself doesn't really matter. You have this Moose tree and you're inserting elements into it. And then once we're done inserting, you simply return the Moose tree. That's how you make a Moose tree. Now, something to consider is what's the running time? Right. So the running time should be pretty simple. You have n elements, so it's going to be n times something, and then each time for each element, you are doing an insert operation. And if we go back here, we notice that insert is actually constant time. So this would be n times big O of 1, which essentially gives you big O of n. So this algorithm, make Moose tree, takes linear time. Cool. Let's go ahead and move on to part 1.2. So here we are going from trees to sorted vectors. So now the question is, you consider the opposite. Let's say instead notice you'll see that it asks you to look at lecture 12, slide 15 through 27. And then it does give you another hint that moose tree is a kind of binary search tree, so you can access the root by calling moosetree.root. So, we're probably going to use something t.root, right? That's how we would get the root of the tree. And, let's take a look at these slides. So we're looking at lecture 12. So we head on over to lecture 12. Let's jump right there. So let's go ahead and open up the PowerPoint. Let's take a look. So this was part of the hint. So we would look at 15 through 27. Scrolling down, we do see slide 15 is here, and it actually looks at this pseudocode, which says, here is a way to take a tree and output the elements in sorted order. So we actually can walk through these slides, and you can notice that essentially what you do is you call yourself recursively on the left side of the tree, and then you print the key itself, or in our case, we would add it to our array A, and then you call yourself recursively on the right side of the tree, then eventually you end up printing 2, 3, 4, 5. You end up printing the array in sorted order because you've inserted it into the tree. And again, moose trees are binary search trees, okay? So that means that the left side is smaller. All of the elements on the left side are smaller than the root, and all the elements on the right are bigger than the root. So this might actually be pretty straightforward, which is the first thing we want to do is we want to look at the root of the tree and see if that is nil. So if the root is not nil, which means we have not gotten to a null pointer, then as the pseudocode shows over here, the very first thing we're going to do is we're going to get all the elements from our left child of the tree and put them all into A. So this, gets all elements from left side and puts them into A in sorted order, let's assume. Then we are going to add our element, so t dot root. So we're going to get, because it's not nil, so we know it's something. So we're going to add our element to the A, and then we're going to call ourselves on the right child of A. So again, this is going to add all elements from the right in sorted order. And you can imagine this works perfectly fine. So again, this is a very, very good algorithm, and it's recursive. So essentially, because it adds the left side in sorted order, and we know the left side is smaller than the root, then we know that we can add the root afterwards, and then we can add the elements from the right side. So this is actually a very, very good algorithm here. Now the question after this, if we go back to our homework, is essentially, give us the pseudocode and also give us the running time. So if you were looking at the slide, this also told you the running time was O of n, but you can actually make an argument for yourself here, right? Assuming pushback is constant time, so assume this is O of 1, which it is, appending an element to a list is constant time, adding an element to the end of a vector is constant time, then you can kind of tell, you call yourself recursively, so you might think, hey, maybe I need to use master theorem here or something, but another way to think about it is that you visit each node at most twice, right? So for each node, you visited at most twice, which means the running time in the number of nodes is 2n, which is O of n. So again, this gives you another algorithm whose running time is O of n. Then we get to question 1.3, which is basically, you think the moose's logic is a little bit loosey-goosey. How do you know that the moose is wrong? Essentially, here we're just expecting an argument to use your results from the sections above to write a short explanation as to why the moose is wrong, which basically is like, why is this data structure just set one, two, dot, 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 k. Now the other thing is you don't have access to this list, so you cannot see what the elements actually are. You cannot see what A is. There is nothing you can do to access A. So if your algorithm does something like A sub 0, you cannot do this. You cannot, if you try to access the 0th element, you cannot do this, okay? It is impossible. There is no way for you to look to see at any element within A, right? So again, you don't have direct access to the list. However, there's a duck. Here's the duck. This is a really cute duck. He's a little cutie. He's such a good duck. So the duck does know what A is, okay? So in his head, he knows exactly what A is. The problem is that you can only ask him yes/no questions, okay? So there's a duck that knows A, and you can ask yes/no questions. So basically, and the duck will tell you the truth. So for example, here you could ask the duck, are there more ones or two? Are there more ones than twos? Okay, so this has to be a yes or no, and then he will say, well, there's 1, 2, 3, 4 ones and 1, 2, 3, 4 twos. So your question was ill specified. Are there more ones than twos? I think the answer here is no, because I think what you should have asked is like, are there strictly more ones than twos? Then you would actually know for sure that there's strictly more of them. You can ask something like, are there two ones? Are there two ones? And he'll tell you no. You can ask, are there 5 ones? And he'll tell you no. You can ask, are there 4 ones? And he'll tell you, yes, there are. Okay, so this is actually maybe pointing you in a direction of what kind of questions you might want to ask for your algorithm. But anyway, we're still trying to understand the problem statement here. So again, this is the problem statement. You have an array of length n with elements from 1 through k. You cannot access the array. It is invalid for you to access the array. However, there's a duck, and you can ask the cutie, little beautiful duck any yes/no question, and he will tell you yes or no, and his answer will be correct. Okay. Your goal. Oh, and here's the other thing. So it takes one bandito burrito. Okay, so for each question you ask, you have to give the duck a bandito burrito. Okay, and you're kind of like a poor college student, so you don't want to give him that many bandito burritos. Okay, so what we're doing is we're actually going to try to design an algorithm that uses the duck. Okay, so you can ask the duck whatever you want. You don't care how the duck works or how the duck knows. You can ask the duck any yes or no question, we start at 1, we go up to k. How many i's are there? Right? So already, this is kind of what we're trying to figure out. So you can imagine writing an algorithm, which is something like, sort or write sorted A, which takes us input A, takes us input N, so you actually know the size of A ahead of time. It also takes us input K, which is how many elements there could be in A. So you can assume, so you don't have to assume, you can actually figure these numbers out, but, yeah, as I gave you in the problem, you can assume that you know N and K. Technically, this is not necessary, and I'll tell you guys after we sort of walk through the solution why it's not necessary for you to assume that you know them. But let's start with the solution where you know N and you know K, right? So that means we can write this quick pseudocode that we have here, where we're saying, well, what we're going to do is we want to figure out, essentially, we would want to do something like this. Let's ask our Doug, how many of I are there in A? Ideally, like if we could do this, so we could just ask him for this number, like how many are there, then to the problem, which is the more interesting one. So essentially you can, we calculate the range, and then what we're trying to do, or the idea here, is this has to run, this has to run in O of log n time. That's the only way that you're going to get k log n time for the full algorithm, for this full algorithm. So essentially we need to split our space in two. So something we can do is we can say, well, duck, let's ask duck, and we can only ask yes no questions. So let's say, hey duck, does I occur between start guess and start guess plus range divided by 2 times, right? So this is the question we're gonna ask them. So this is a yes no question, right? This is not asking them how many times does it occur. This is asking them, does it occur? Does the number of times it occur fall between my starting guess and my starting guess plus range divided by 2? So what does this mean? Let's say, at the very beginning, our starting guess is basically 0 and n. So what this is going to be asking is, does I occur between 0 and n divided by 2 times, right? Or it'll actually be n plus 1 divided by 2, which is essentially halfway. So we're trying to go up to half of our possible guesses, and we're going to ask them, does it occur this many times, right? Now, the other question we can ask, or you should immediately know, is you can also ask your duck. So let's say this is response 1, response 2. We can give it A, and we can say, does I occur between start guess plus range divided by 2 plus 1 and n guess times. So again, for our example, where we started with our guesses anywhere between 0 and n, this would ask, does I occur between n plus 1 divided by 2 plus 1, right? So we're not including this guess anymore. We're going to the next guess, and n, which is our nth guess. So you can see that this is basically asking the duck, I think the number of times, 3 occurs is going to be, either 0, it's going to be 0, 1, 2, 3. So this array is of length 6. So it's going to be 0, 3 can occur either 0, 1, 2, 3, 4, 5, or 6 times, right? And these are all my possible guesses. And basically, I'm asking the duck, okay, so n in this case is 7. So then range is going to be 6, 6 minus 0 plus 1, it's going to be 7. So I'm going to ask my duck, my first question is going to be, does 3 occur between 0 and 7 divided by 2, which we're going to round down, so that gives you 3 times. Or does 3 occur between 4 and 6 times, right? So these are 2 yes-no questions. And actually, it should be pretty obvious to you that one of these must be yes, right? There is no in between. Either the first one is yes or the second one is yes. Because it either occurs 0, 1, 2, or 3 times, or it occurs 4, 5, and 6 times, right? So, and that splits our space in half, right? So now we can say, well, if, the answer to the first one is yes, if the duck said yes, then I can actually call myself recursively on start guess, right? So now our guess is going to be 0 to 3 instead of 0 to 6. So start guess, and then let's zoom out a little bit. We see start guess and start guess plus range divided by 2, right? Otherwise, if his response is yes to the second question, then that means I call myself recursively, but instead of start guess, here we would do start guess. So our starting guess is actually the second half of the array, or the second half of our guess space, like our possible space of answers, and then this is the last one. And then obviously, we cannot this function is called, it asks two questions. You know, it asks about the left and the right. So it asks two questions every time it's called. So now the question is, how many times is it called before I get to an answer, before I get to the right answer? And the way to look at that is that essentially we need a base case. So the base case is if my start guess equals my end guess, right? So totally forgot about this. So if my start guess equals my end guess, then I return my start guess. So if my guesses are equal, then that means I've narrowed it down to exactly one of the answers, right? So again, for this example here, the duck would answer yes to this question, to this first one. Does 3 occur between 0 and 3 times? So then we would call ourselves recursively, you know, guessing, well, it's going to be 0, 1, 2, or 3. And then here we would ask two questions. We would say, does 3 occur between 0 and 1 time? And we would also ask, does 3 occur between 2 and 3 times? And again, 3 actually occurs 2 times, so he would answer yes to the second question, right? This one he would say yes, which now means our guesses are either 2 or 3. It either occurs 2 or 3 times, right? So then here we would call again ourselves recursively. We would say, does 3 occur between 2 and 2 times? Or does 3 occur between 3 and 3 times? And obviously the answer to this one is yes, while the answer to this one is no. So, and then we know, because our guess is between 3 and 3, we know that our answer, it actually occurs exactly 2 times. So this is yes, and we know that our answer is 2. So from that point of view, you can already see that we split the possible space of answers in half each time, which means this basically takes log of n, because how big is our range at the beginning? It's from 0 to n, and each time we split it in half, so it's going to take log n of that many splits in order to get to the very end, and then once we get to the very end, we'll have our answer because we'll hit this base case where our guesses are exactly equal to each other. And that's it. So that takes log of n, which means you only have to pay, you know, it takes 2 times log of n or something like that, so you'll have to pay, you know, 2 log n bandito burritos to your duck. However, if we go back here, we talked about how the actual algorithm, so this is the actual pseudocode, this is our helper method, which is pretty complicated, but this is our helper method and we kind of need it. So if we erase all these examples, we would have the pseudocode looking something like this, and the running time would be k log n. To the last section of the homework, this is exercise 3, where we cover hash functions. So basically here what we're going to be looking at is your understanding of good hash functions versus good hash families versus bad hash families versus bad hash functions. So if you're still having a little bit of trouble with this, I encourage you to head on over to the lectures and take a look at hashing and hash tables, as well as universal hash families here. So you can actually open up the slides in PDF format, and this is actually going to come in quite in handy as we cover some of this stuff. But essentially, the first question is asking you about a new hash function. So we have a hash table of size 80, as the question states, and we are given a hash function, which is the sum of the digits of n. So the hash function is h of n, and this is going to be the sum of the digits of n. And they give us a few examples. I guess another thing to keep in mind for this problem is that our universe is all student banner IDs. And a banner ID, if you guys know from NCAD, is a 9-digit number. Okay, so basically we're looking at our universe is of size 10 to the 9th, which is actually pretty big. That's essentially 1 billion possible elements that we have, because we have a 9-digit number, and then there's 10 possibilities for each spot in the number, right? So this spot can be 0 through 9, 0 through 9, 0 through 9, etc., etc. So for 3.1, we're given that we have a hash table of size 80. So you can imagine that hashing a billion elements into a hash table of size 80 is a little bit questionable. However, we do know that there are at most 217 students. So we're really only going to be hashing 217 into this hash table of size 80, which means, we expect there to be around like 2 or 3 elements per bucket. All right. But anyway, we're given a hash function, which is h of n, which is equal to the sum of the digits of n. And we're given a few examples. So for example, we've had the hash of 0, 0, 0. This would be 0 because they add up to 0. The hash of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This would actually add up to 36 because when you add up these numbers, they add up to 36. And we should drop the 9 because that's too long. Okay. And then the question here is like, is this a good hash function? List 2 reasons supporting your answer. So I encourage you to pause the video and think, is this a good hash function or not? Cool. If you're back, then it should be pretty clear to you that this is a terrible hash function. I mean, the first reason is it's deterministic. No randomness. So basically, your adversary can create inputs to the hash function that all hash to the same thing. What does it mean to hash to the same thing? That means that the sum of the digits is the same, right? So you could do h10000 is equal to h of 0100000 is equal to h of 0010000, right? So all of these, the digits add up to 1, and they're all equal to each other, and there's like 9 of them, right? And there's actually a lot more. Like if you think like 1, 2, 3, 4, 5, 6, 7, 8, like this actually gets you to another example where these numbers add up to 36, but there's a lot of different numbers that add up to 36, right? So one, it's pretty bad because it's deterministic. It's not random, which means somebody can very easily come up with a sequence of elements to insert that will all hash to the same bucket. Now, the other problem, which maybe you thought of, but is also kind of like an implementation detail, is, well, the hash of 9999999 is 81. But our hash table is of size 80. So this is a bad hash function for this hash table because we are actually going to try to index outside of our hash table if somebody gives us this ID. And then the other thing that we alluded to is like, this is not uniform. Even if this hash function didn't have these other issues, there is only one value that hashes to 0. Only one. Only one in our entire universe of values hashes to 0. And that is the value that has all zeros, right? And there's only one of them. But, there are many values that hash to 36, for example, right? We have 0, 1, 2, 3, 4, 5 hashes to 36. We have, let's add 1 here and let's remove this 0. So this also hashes to 36. And then we have, this hashes to 36. And we have, this hashes to 36. And essentially, you have a lot of numbers, like this one hashes to 36 too. And this one hashes to 36, right? So you have a lot of numbers that hash to 36, but you only have one that hashes to 0. So you can immediately tell that this is actually not uniform, right? So there are some numbers, there are some buckets that get more elements. So these are reasons why this is a pretty bad hash function. Great. So we do make an improvement on the next question. We say, well, let's not consider a single hash function. Let's fix the randomness, right? So 3.2 is basically like, let's fix the randomness, right? The random issue. So instead, what we say is, well, let's define a bunch of functions. So for m1 into 1,000, so this is, you're going to define 1,000 functions. So you're going to have 1,000 functions, and they are going to be given by, h of m is equal to m times x. So my hash function, whatever the input is, there's going to be 1, so there's going to be like h of 1 is equal to x. h2 of x is equal to 2x. h3 of x is equal to 3x. And so on. We have 1,000 of these. h1000 of x is equal to 1000x, right? So we have 1,000 of these, basically. Okay, so now we have a hash family. So we have a family of functions. And the way we're going to use these is we're going to randomly pick one of the functions and then use that for our hash table. So this actually fixes the random issue because you don't know which of these functions you're going to pick ahead of time. So this fixes the randomness issue that we ran into in 3.1. Furthermore, it also fixes the issue with the buckets because now we have 99 buckets, and essentially our functions are actually mod 100. So we will never index outside of the bucket. So intuitively, this kind of looks like a pretty good hash function. So I'll let you pause the video and think about, is it really a good hash family? Is this a good family of hash functions? So hopefully you've come back after you pause the video, and I'll let you know that no. This is a bad hash family. And that's because it's small, so that's good. So the family itself is small, right? There's only 1,000 of them, and we can tell which function we're going to use by just storing the single value m that we picked. So it's pretty small, it's pretty good. So that's not why it's a bad hash family. We did say that the hash function itself is sort of okay as well, and we got, now it's random, so it's not deterministic, right? The way we pick it is random. However, we do also need that the probability of two elements, so let's say ID I and IDJ hashing to the same element, right? So this is the whole point we're trying to use hash functions. We want the probability of two elements going to the same bucket to be small. What do we mean by small? We want the probability that they go to the same bucket. So the probability of IDI and IDJ going to the same bucket should be less than 1 over n, where n is the number of buckets. So it should be less than 1 over 99. Basically what this tells us is that the probability of any two IDs colliding with each other is uniform in all of our possible buckets, right? Like this is the best you could hope for. If it's less than 1 over 99, then basically our hash function, our hash family is very, very good. However, if we think about this, is this less than 1 over 99? Is the probability pretty small? So if I randomly pick one of our HM, is it true that the probability that two elements collide is small, right? That's what we're looking for, where these two elements are different. So the probability that they collide is small. And again, the answer to this is no. And the way to prove it, or the way to think about it, is you can think of a counterexample. Suppose, right, so it has to be for all pairs of elements. If I randomly pick one of our HM, is it true that for all pairs of elements, right, so this needs to hold for all pairs of elements IDI and IDJ, right? For all pairs, the probability of them colliding must be small. Now, the answer here is this is not true, because you can actually come up with a pretty easy example. Let's say I have ID 1, 2, 3, 4, 5, 6, 7, 8, 9. So ID 0, 0, 0, 0, 0, 0, and then you have ID 0, 0, 0, 1, 0, 0. Okay, so these two IDs, what I claim is, let's scroll down. No matter what m is, so no matter which hash function I pick, h of IDI, right? So h of this, which is going to be given by m times this mod 100. I mean, it should be pretty clear that this is actually 0, 0. So no matter what, this hash function is always going to give me 0, 0, no matter which hash function I pick. Which also means that no matter which hash function I pick, right, it doesn't matter which one I pick. You can imagine that doing this m times this is essentially m times 100, which mod 100 is also equal to 0, 0, right? Because no matter what, the last two digits of this number, like no matter what m is, right? Like if m is 1, then this is 100 mod 100, right? If m is, 564, then this is 564, 0, 0, right? Because I multiply by 100. So no matter what, the last two digits are going to be 0, 0, which means for these IDs, the probability of them colliding based on our hash family is actually equal to 1, which is bigger than 1 over 99. So this is a bad hash family because there are pairs of elements where no matter what hash function you pick, they will always collide. Yep, so that's about it for this part. Let's go ahead and jump to the coding. So section 4 has some homework. It's a homework thoughts, and then we can jump to the coding one. You can get your starter code, as always, from Replit. So let's take a look at homework. Let's go back to our dashboard. I am working on the Python version. I'll have this out for you sometime next week, hopefully. But yes, here we are. So this is the coding assignment, and let's take a look at our README. So essentially, we've got a couple of problems. The first one is stacking books. So let's cover that one, stacking books. Again, I'm going to write the pseudocode. It's your job to write the C++ code. So do not expect that you're going to be able to just copy this code and use it as a solution. I'm writing the pseudocode for you, or very close to the pseudocode, as we solve it. So here, we want to write a function called find final book stack size. So that's this. And it's actually going to return an integer. And it takes as input, essentially, a queue and a stack. So these are two data structures that you probably want to look up. So it's going to take in a queue of students. Let's zoom out a little bit. Set syntax. Let's try to set the syntax to C++. So let's do this. So this is going to take a queue of students, and it's going to take a stack of books. Okay, and basically this question is actually not very difficult, I would say. It is describing what happens. Like, it gives you a description of something that's happening, and essentially the solution that you want to implement is a solution that does exactly what is being described. There is no trick to this question. The best solution, or the solution we're looking for, is one that just does what is being described. Okay, so essentially here, if we read the description, it says that on library day, fiction, which is represented by a 1, and nonfiction, which is represented by a 0, books are given to students standing in line. The books are in a stack, so this is going to be our stack of books, okay, and are given out in a strict and strange way. On each turn, if the student at the front of the line, so if the student at the front of the queue wants the genre on top of the stack, they will take it and go home. Otherwise, they will get back in line, so they will go to the back of the line. This will continue until there are no books or students left, or none of the students in the line want to take the book on the top, right? And what this function wants to do is how many books are going to be left over. So once all the students are gone, or none of the students want the book at the top of the line, how many books are going to be left over? Essentially, what we're going to do is we're going to implement this iteration that is being described here, right? So what this talks about is on each turn, the student at the front of the line wants the genre at the top of the stack. So we might want to look at, let's get the student at the front of the line. So that's students dot front is going to give you the student at the front of the line. Okay, so students dot front is actually going to give you the student at the front of the line. This does not remove the student. This does not remove the student. It just tells you who is at the front. Okay, then we want to look at the book. So what we would do here So we have books.top, actually. So we should be able to do books.top to see, again, this is not remove, this is to see the book at the top of the stack, right? And then basically, if S is equal to B, so if the student wants the book, so the student is 1 and the book is 1, then we are going to pop the student and we are going to pop the book. So pop actually removes the element at the top of the stack and at the front of the queue. All right, that's great. Otherwise, if they're not equal, then what's going to happen is the student is going to get popped. Okay, so he's moving out of the line, but then he's going to get moved back into the line. So we're going to push him back into the line. So that's student on pop and then student on push. And that's basically the description of what's going on here, right? And it's saying, but it says on each turn. So essentially, what that tells you that this is going to be wrapped in some sort of loop structure, right? So we're going to do it for a while. And the question is like, how long do we do it? Well, it does tell you. They will take it and go home, otherwise they will get back in line. So this continues until there are no books or students left. Okay, so while students.size is bigger than 0 and books.size is bigger than 0. So while these people are still left, then we'll do this, right? And then remember, we want to return something. Go home. There are no books or students left, or none of the students in line want to take the book on top. So that means every student, we went through every student, but nobody wanted to take the book, right? So what that tells me is I need to keep track of how many students have I gone through before without a book being taken, right? So we could say int students tried. We'll start at 0. And basically, every time a student takes the top of the book, we set students tried equal to 0, right? And every time they don't, so this is the case where the student gets popped and he goes back to the line, so he didn't want it, we increment the students tried by 1. And then what we would want to check here is if students tried is bigger or equal to students.size. Right. So I guess what we would want is we want students tried to be less than or equal to students.size. If we haven't tried all the students and there's still students and there's still books, then we keep going. Now, if we ever run out of students or we run out of books or the students tried is greater than students.size, then that means we've tried all of them. We tried all the students, so we're done. And then at the end, we would just return, well, how many books are left, which I think you can just do books.size. Right? It's because we popped them and put them back on, so we just need to know how many books are left. So here is the pseudocode, not possibly incorrect, for question 1. Moving on, we would look at question 2. So this talks about building Lego homes, and this is worth 10 points. So again, for question 2, we actually talk about having n Lego pieces, and each piece is a character in a string Lego bucket. So let's look at the example. So essentially, what you're going to be given is you're going to be given a, our function is count Lego houses, and we're going to be given a string, which is a bucket. Okay, so some sort of bucket, and these buckets, right? A few examples are basically this, which basically represents, that we have three B's and 2 A's. Okay, and then we're also going to be given a string, which we're going to call a blueprint. Cool. So let's see what's an example of a blueprint here. So this is an example of a blueprint, which basically says that to build one house, we need 1 A and 2 B's, right? So you can imagine you would actually use this as an algorithm to figure out, do you have enough material to build as many houses as you want to build, right? It's a very reasonable question. We're going to return an integer, which is just, do I have enough material to build the houses I need to build? And essentially, now that you understand the problem, which is given the blueprint, which tells me how many things are needed to build one house, and given a bucket, which tells me how many things do I have, your goal is to work through all of this to figure out how many houses can you build, right? So intuitively, you could imagine that the pseudocode is something like, well, if I need 1A to build one house, you might want to know how many A's do I have? Because that tells you, well, you can build, at most, the number of A's you have, right? You could also say, well, if I need 2 B's to build a house, then I can build at most, all the B's I have divided by 2, because I'm going to take 2 to build the house, right? So intuitively, this already tells you, well, something I really want to be able to know is I want to be able to figure out how many of each letter do I have and how many of each letter do I need, right? And then a very intuitive data structure, if you want to think about it that way, or just one way to figure this out and to save it, because you're going to want to save it because you want to look it up different times, is to use a standard unordered map from characters to integers. So this is going to be a map from your character to how many times it occurred in something. Okay. To help out, we're actually going to write a helper function whose job it is count the number of characters in a string. So count string, and you could say this takes a string as input. Let's call it value. And what we're going to do is we're going to iterate for each element in my string, right? Let's create our map. Make sure it's empty. Start out as empty. Let's call it counts, right? So we create our map. It starts as empty for each element. We check to see if it's already in the map. So if counts.count of the element is 0, that means it is not in the map. So we can say, well, okay, counts of element is equal to 1 because we've seen you one time. Otherwise, it is already in the map, so we say, well, counts of element plus plus. And then we return counts. So again, this is some pseudocode / C++ code for how you might count the string. There may be some errors here. I encourage you to understand what the code is doing to help you out. But essentially what this does, it takes a string and it gives you a map telling you how many times each character occurred in that string. So going back to our original problem, that's exactly, this function is exactly what we needed, because we can say blueprint counts is count string of my blueprint, and let's call this auto just to save a little bit of space. We can say Lego counts is count string of my bucket, right? So this tells me how many, for every character, how many do I need to build one house? That's what BP counts tells me. And this tells me for every character, how many do I have in my bucket? So you can imagine what we want to do next is essentially figure out, you can imagine, let's keep a vector of integers, which is going to be how many with each character, or something like that. And what we'll do is we can iterate over our blueprint, right? So this is iterating over each element in our blueprint, which means essentially you can also write it this way if you're using, well, yeah, I think we're using C++17, so you should be able to write it this way as well, which tells you letter and count. So this will actually tell you each letter and the corresponding count inside of our map here for the blueprint. So what we would want to do is we want to check, well, do we have any of these in our Legos? Like, do we even have any A's in our bucket, right? So we would count how many of the letter we have, and if that's 0, then we can immediately return 0. Because we cannot build this house. We don't have any A's in the bucket, and it requires at least one A. That's the only way it would be in our count map, blueprint count, right? Otherwise, here, we can actually check to see, well, how many do we have, right? So you can actually say houses I can build is actually given directly by Lego counts letter. So basically, how many of this letter do I have in my bucket divided by the count it takes me to build one house. So this tells me how many houses I can build. So if I have 10 A's and it takes me 3 A's to build one house, this will be 3. So it tells me it takes 3 houses to build. Houses I can build basically tells you how many houses you can build for that specific character. So what we're going to do for that specific letter is actually we're just going to keep track of all of these. So we could say something, push back, houses I can build, for example. And then, now that we know all the different houses we can build, at most, with each character, we can just iterate through them and kind of find the minimum, right? So one thing we do want to keep in mind here is it is possible that we're given an empty BP counts. So I believe you're supposed to handle that somewhere. I encourage you to read the instructions, but what I'll do here first is I'll handle it. I'll check this. I need to make sure the size is bigger than, if it's equal to 0, so this is empty, I think this is supposed to be, I throw something. I forget exactly what. But then what I can do is actually, I can set the current min to be how many characters can I build? 0, and then I can iterate over these values, and then basically if current min is bigger than count, then current min equals count, and I return my current min at the end, which gives me the minimum out of all the possible ones. So this is one valid solution here. That's great. Moving on to the next question. Again, all of this code is essentially pseudocode, so I wouldn't necessarily copy paste it and try to use it. You need to understand how it works. The next question is actually fairly interesting. We are going to be working with a data structure called a trie. So the way a trie works is essentially it's a tree. It's a tree that could have many, many children. So you can actually look in treenode.h. So let's take a look there. Treenode.h is the one that defines the trie. You are asked not to change anything in this file. But basically, a tree node is a class in C++. You don't have to worry about this. This just means that it can handle, the T is just, instead of writing int or string or whatever, now we can write T, and C++ will know what to do with that. It's called polymorphism. But essentially, we have a tree node. Here's the constructor for the tree node. It can either take in a value and just sets its value. This property value is private. It sets it equal to the value you give it. Or it can take a value and a vector of pointers to other tree nodes who are the children, right? So this is the children here. Instead of having just the left pointer and a right pointer, we're actually going to have a vector of pointers to other tree nodes, all right? And again, this is private, so you can't access it directly, but you can access get value will return to you the value, and get children will return to you this vector of pointers. And then you can also check to see if the tree node is a leaf, which we define as a leaf is one that has no children. So if you have no children, then you are a leaf, right? And then basically what we want you to do is, if you understand that, then you understand the entire trie. You can look at this function free tree to kind of get a sense of like how might you recursively try to solve some of these problems, right? So this function is actually recursive. It first checks the base case, which is if my node is a null pointer, then I'm done. Otherwise, it frees all of the children, and then it deletes itself. Yeah. So going back here, a trie, essentially, we're going to use it as a data structure where we can store words. And it's a really fast data structure for looking up words, basically, because what we'll do is within each node of the trie, we're going to store a single character. And for example, here's a trie that holds the word acid. So if you go here, you have A, C, I, D, and then $, which means the word has ended. So that's acid. It also holds the word act. So A, C, T, act. But you can imagine there's a pretty efficient way to store a large number of words, because if they have a common prefix, then they actually share the same character, right? So in a sense, we have acid, we have act, we have actor, we have ace, we have 4 different words, all of which are using only A and C. Like there's only one character A, one character C. So this does not get duplicated. And it's the same for the other words that we have here. So that's what a trie looks like. This one has ace, acid, act, actor, bee, beat, bear, cab, and cob. Okay. Now we did talk about like to look up whether a word is in the dictionary or it's in the trie. We simply traverse the trie to see whether the word is in the trie. To add a word in the dictionary, we insert it into the trie. Although we won't implement it in this homework, you can imagine how tries can also be used to implement autocomplete functionality. So you can imagine if somebody's typing AC, you can very easily know what are the possible words that are after they typed AC. So this is actually how autocomplete is implemented across many different services, if you've ever seen that. All of the below should be implemented in instance.cpp. So let's get started. So question 3.a is essentially asking you to write a method, which is valid word. So this is the crux of the spell checking functionality, basically given a trie. So let's start writing this. So this is for 3a. Essentially, it's going to return, I think it's going to return an integer, apparently. Well, let's go with Boolean. It's going to return whether it's valid. So if it's valid, and it's going to take in a trie as our dictionary, right? So it's going to be given a trie, and we can actually look at the signature here. So 3a is valid. It's going to take in a tree node of characters. So this is how we would write it, and it's going to take in a string, which is going to be a word, and it wants to know, is this word inside this dictionary, right? That's essentially what we're trying to check is the word inside the trie. So I encourage you to pause the video and think about that for a second as to how you would check to see if the word ace, for example, is in this tree, right? Cool. Okay, so hopefully you came back. A couple of things that we want to consider is we want to have some base cases, but let's start with the not base case first. So as we can see, if we start with ace, really what we want to do is we want to look at all of our children, right, A, B, C, and we want to see if any of them have the letter A. If that's the case, then we might imagine that we can recurse on the rest of the letter, right? So instead of looking for ace, we can actually look at all the children of our root and see if CE is valid, right? So something we could do here is we can say, well, let's take a look at each child. So something like this. I think get children is the function that we're looking for. So the tree node for each child, if word, I think this is valid syntax. If word 0 is equal to child.getValue, right? So if this character, if they're equal to this character, then we want to check if the remaining of the word is valid. So we would call ourselves recursively on the child with the rest of the word. So starting at 1. This might not be valid syntax, so I encourage you to check, but this is essentially, something that you might want to do. And then basically, we're trying to check if it is valid at the remaining of the word. If it is not valid, then this word does not exist in the dictionary, right? So we can actually simply return whether it is valid or not. And this is not our base case, right? So you can imagine that essentially we're looking at all of the children, and for each child, we're trying to see, okay, are you equal to the first word? So we start here, we look at all the children, we see if they're equal to A. If they are equal to A, then we want to keep going down the tree to figure out, okay, are all the children of A, are any of the children of A equal to C? And we keep going down the tree, and we say, well, are any of the children of C equal to E? And if they are equal to E, then we want to check, are any of the children of A equal to this $sign? So that actually gives us sort of the endpoint, the base case, which is if word.size is 0, then we want to return whether dict.getValue, right, is equal to this $sign. So if it is equal to this $sign, then it is a child. If it's not, it is not equal. So something else that you want to keep in mind here, however, is that this dict, you're indexing into it. So there is another base case, which is if dict is null pointer, right? So if we got to the point where our child, so this is our child, we should actually never hit this case because we only ever call ourselves on valid children. So I don't believe you have to worry about this. Got it. But you do have to worry about the case where you finish doing all of this. So the word set is not 0. You look through all the children, and none of the children matched, in which case you simply return false. Cool. So this is probably an approach to it. You guys should definitely think through all these cases. I'm not 100% sure if the child is going to be null here, but you should definitely think through all of them. Cool. The next one is basically adding a word to the try. So you can imagine adding a word is actually going to be quite similar to isValid. So we're going to take a tree node of characters. This is going to be our dictionary, and we're going to take a word that we want to add. And then immediately you could say, well, the very first thing we want to do is we want to add a new word to the dictionary and returns whether the insertion actually happened. That is to say, if the word is already present, the message should return false and leave the tree unaltered. So basically, if isValid dict word, so if it's already in the dictionary, then we return false and we do nothing else. Otherwise, we want to do a little bit of recursion. So in this case, just to avoid having to do this isValid check every single time, I'm actually going to define a helper method. Let's call it helper. That takes in the exact same inputs. But here we know the word is definitely not valid, so we're going to insert it no matter what. Right? And this is what we're going to call it here. Add word helper dict word. And that's just because I want to avoid having to do this check every time I call the function. Right? So for the add word helper, again, this dict is going to be our root, so it's going to start here. And basically what we're going to do is we want to look through the children to see if the character already exists. Right? So if it already exists, we want to reuse it. If it doesn't exist, then we need to add it. So essentially, we would iterate over each child. So I would say dict get children. And again, the first thing you should ask here is like, what if dict is null pointer, right? So what if I'm being passed a null pointer? However, we'll see that will probably never be the case. But again, just that's something to keep in mind that you should ask yourself. We're trying to code this live. So we iterate over these children. We get the child. And basically what we're looking to see is we want to see if the child, if its value is equal to word 0. So if it's the beginning of our words, for example, ace, or let's say we're trying, act didn't exist and we're trying to act, or all these words exist and we're trying to add aced, then if it does already exist, we kind of want to recurse and add the word to that child, but only the smaller word. So word dot substring 1 or something like that. So we go from 1 to the end of the word, right? Yes, and we would essentially return this. So we want to recurse on that one. Yes, that seems reasonable to me. So we check every child if the child is equal to the value. Otherwise, we went through all the children and none of them matched. Oh no, none of them matched. So what does that mean? That means that we're probably trying to act something like dandelion. So we need to add a D. So we're actually having to create a completely new tree. So what we need to do is we need to look at our dictionary and we need to add a child. So let's actually see what's the best way to do that. So we look at tree.h here. We see that our tree has, it does have, it can check if it's a leaf, and it does have, okay, the get children will let you get the children and immediately add it, so it is immutable. So we would do get children. Get children returns a vector of pointers, and then here is where we would push back essentially a new tree. So let's create that new tree. We would say new tree node with a character. Here it is. So new tree is this. And I guess the value we would give it is actually word 0. So we create an empty tree that has just the first character in the word because it was not in any of the children. Then we add that tree to be a child of our parent. So we push it back here. And then we call ourselves recursively on this new tree because now we want to add the rest of the word, whatever that is. Okay? So this, if the dict is null pointer, so again, you're never going to get an input that's null pointer because we're always checking, we're only looking at valid children. Although it is nice to, you should probably check that they're not null pointers. There's some stuff to be done there. But the other thing is we do have a base case where the word runs out. So again, if word.size is equal to 0, so that actually means that we have no more letters to add. So whatever node we're in that we just added, we have no more letters to be added here. So essentially, if we go back to our example, let's say we wanted to add just the letter D. So we started at the root, we iterated, we didn't find anything. So then we added the letter D, we call ourselves on that new tree, and now this is empty, which really means that we just need to add a single child telling us that we are now at the end. So we would add a final, which is going to be a new tree node of characters. Which is going to have a $sign in it because this signifies that we're at the end. And we're going to add that to our child node here. So we are going to push back this final node, which also has no children. I believe those are the primary cases for when this is empty. All right, so that's for 3B. And again, that code might not be complete. I encourage you to double check it and make sure it looks complete. Question 3C is dict equal. So what this wants to do is it wants to define a function that takes in 2 tries. Right? So here, Q3C, we want to take a function which takes 2 tries. So dict equal. And you can imagine we take in this try and we take in another try, and we don't want to change them. Let's say right-hand side, left-hand side. We don't want to change the tries, but what we do want to do is we want to tell if they're the same try. And again, we don't want to compare the pointers themselves. They can be different tries, but we want to know if they have the same content. Okay? So if the two tries have the same content. And again, the assumption here is we're going to avoid passing in any null pointers from the get-go. All right? So, but again, you should always think about that. Could the pointers be null? Okay? But basically, the very first thing is there's a very simple base case, which is if the left-hand side get children dot size does not equal the right-hand side get children dot size. So if the number of children is not the same, then we can immediately return false because we know that the two tries are not equal. Like one of them has more, one node has more children than the other. Otherwise, we do have the same number of children. And now what we want to do is we want to figure out if the children have the same content. So probably the best way to do this, I encourage you to pause it, but you can think about this, is to create a map from child character to the try starting at that child, so to the child self, right? So we'll do this both for the left-hand side and for the right-hand side. So you might create an unordered map from character to tree node pointer, left-hand side map. And you will do something similar for the right-hand side map. And now we can iterate over the children. So for child and left-hand side get children. And similarly for child and right-hand side get children. We want to add this child's value. So say get value. And we want to set that pointing to the child itself. Right? So this is how we're going to tell that all the children, because all the children should be pointing at characters. That's how we're going to be able to look up the same characters from each side. So actually, we can do this just for the left-hand side. Yeah, so let's do it just for the left-hand side. And we add it to the map where it's equal to the child. And then what we can do is we can actually iterate over the right-hand side. Right? So they're equal. And we know the children are the same. So what we want to do is we want to check to see if the left-hand side has a child with the same value, or let's say it doesn't have a child with the same value, then we're actually done. We can immediately return false because we found two children that don't match up, right? Otherwise, it does have a child with the same value. So we want to get that child. And we want to see if that child is equal to the right-hand side child. So we get this child, and we pass it in into dict equal to see if they're equal. And if they're not equal, then we want to return false because we're done. So if the child didn't exist, then return false. If you compare them, right, recursively, because these are two tries themselves, if they're not equal, then you also return false. Otherwise, if you look through all the children and none of them were not equal, then it must be that things are equal, so you return true. Now, again, this might not be the complete implementation. This is being done on the fly, but I encourage you guys to try it out and see.